and machine. Specifically, this session is for the machine learning project, and yeah, we've been working on this project. It's a group of software engineers, and we've been working on this project for months. And here I present to you what we have come up with this series. So this is majorly machine learning architecture for smart mechanic matching using binary classification for a service records in Uganda's informal automotive sector. With this is a record, and some of our keywords are the binary classification, machine learning, and mechanic matching. Uganda as an area we specify in, we specialize in, and sharp explainability of data rows, and XGBoost as one of our models, and many more models to come. These are my group members, me, Bronya, Patricia, and Naisanga. So basically, this is some of the contents of our presentation as I'm going to be taking you through. And to get started for the background and introduction of our project, it's majorly more of trying to explain how it takes us through the Uganda's vehicle repair sector, and which is largely informal, no certification or accountability for repairs. And it's made up of drivers, border riders frequently who get overcharged and are poorly served when they are servicing their vehicles. And currenting match, we normally use word of mouth and only, no data or persistent trust or deficit. We are totally analog. And this is where Motofix, a machine learning based smart mechanic matching via binary classification comes in, and it predicts a good match or a bad match with the nearest location or geographical location, so that we save a lot of time and save more vehicles. It is more based on a 20 million record and record data set, whereby we sampled the first 50 and we try to work with that because the data was too big. So it brings us to our problem statement that defines our domain and informal mechanic matching in Kampala with no data accountability and persistent trust, and gives us where we managed to come up with a binary a computational problem, the binary classification, where when we predict a good match, it comes as a 1, and not a good match 0 from the 13 service records in our data set. And so to take you more through our methodology or system architecture, how this is going to work, it starts from the whole pipeline starts from our service request. So where you put in vehicle type, issue, location, agency, how urgent is it, and then there is data preprocessing and cleaning, feature engineering, and model prediction, and which came up with a success probability, output probability score of a good match. And also then the mechanic ranking and selection based on the ratings, and we sort by the probability applying business. And then the output is a matched mechanic plus a confidence. So we don't just give you a matched, not just a mechanic, but there is a reason as to why that mechanic has been matched, and alternative candidates left there, like the second options that you may wish to get in touch to in case the first option fails. And then the feedback loop, the more feedback people give on a given mechanic, it goes in the data, and our model, it retrains our model the more so for post repair ratings. So according to our data set, some of the exploratory data analysis is we had some data leakages in our data set, and the class distribution showing, as you can see from the class distribution, 60% of not good match and 61% not good match versus this 31 good match. That has a totally classy balance, and a model cannot train when it's like that. So we come up with solutions, and I'm going to show in the next slide. The target class distribution was 61.1, which is not good match, and on basing on our record count, and we got it from the sample we got, and we had the 38.9 good match, which brings that to a distribution split, as you can see, and some of the correlation matrix based on the records, mileage, distance, match, and duration. So we came these three leakages were addressed through the following through the following ways: temporal preprocessing and sampling contamination, whereby we had to come up with 80 to 30 stratified split, 40K train and tested stratified, and preserve 61% to 39 class imbalance across both data sets. And now when you go through our model comparisons, because basically we had 8 models. So that is logistic regression, decision trees, random forest, and XGBoost, support vector machine accuracy, k-nearest neighbors, and naive bias, and neural network accuracy with all the confusion matrices. They are well displayed depending on the good match. I mean the how they performed. And predicting the good matches, the false positives, and these as well were the ones we based on to predict to get our best model, which was the logistic regression due to its accuracy, and it was not based on its accuracy, and we based on the F1 score, being that we're dealing with binary data. So the models were evaluated in these metrics: accuracy, precision, recall, and F1 score. H value meaning this is. Now in this table we look at the best model prediction and what it nearly means and how we came up to make it the best of it all, what we gauged on. So the accuracy of 51.6 barely above random and weak feature signals, that's what it means, and the precision 39.5 model over predicts good matches, and also the 46.1, it misses greater than 50% of the quality mechanics. Moderate reflects synthetic data limits, that is for the 0.426 F1 score, and the ROC arc of 0.511, near random chances of 0.5. And all models lack strong discriminative signal. The pipeline to our deployment and MLOps logistic regression was the model with those metrics, F1 score 0.4, ALK 0.6, and with the training time of 1.23 seconds, tracking all the models logged to the ML with Odystray. The pipeline was the Colab, MLflow, Streamlight, and Cloud. So our interface real-time predictions are via drop-down sliders that are interface. Now we also have the image below, and also controls, input, validation, error handling, predicting logs, and data version control. And also monitor weekly batch evaluation to retrain the alpha and drop. So this is the MLOps pipeline showed in image form, from raw data, preprocessing, split data, scale features, training models, evaluating them, selecting the best model. We compressed them. We compressed them to realize and deploy the API, and mobile app MotorFix users or border riders get access to this system, and also we monitor it and track. So we keep on retraining according to the data we have. So this is our interface basically, where it's just self-explanatory. You put in the car, the vehicle type, the service, the urgency level, the customer type, the cost, what. So when you hit, it processes the results, and you see whether you have a good match, and the mechanic is recommended for this service. So this input summary. Some of our limitation were that the sampling bias risk of the 50K of the 2 million records. That's why we had a lot of data imbalances, because it was just, and we had to overcome it through the technical measures that I explained above, and the synthetic data set limit the real world applicability. Models rely on transactional features only, not mechanical identity or signal captures. And not only limitation, we also had key achievements of our F1 score of 0.4, the data set, which is the 50,000 records, and the training time of 0.5. And what's next? We plan on checking how satisfied users are with MotorFix. Also, the prototype, the Streamlight version, is now live for the real world testing. And other features, it includes protection against the data leakage and host-sensitive bleaching, balancing, and sharp explainability. Some of our roadmaps are the time series fly features to analyze mechanic performance, geospatial signals to reduce travel time and effort, multitask learning to improve the quality and service cost, fairness constraint to the buyers. We, out of the 8 models that mentioned above, each model had its own architecture as listed and explained below, where logistic regression came up with L2 reg C, which is 0.1, LBFG solver, and class weighting balanced decision tree, which and the training time of 0.56 seconds, and F1 score of 0.4, which is a deployed model. Okay? And the decision trees are Guinea impurity splits and a max depth of 10, balance weights and early splits on the cost sharp explainability confirmed. And the training time was 1.25, and each F1 score was 0.3. And the random forest with basing on 100 trees, and its bootstrap aggregation or max depth was 10, balanced features and features subsampling and at each split. So the XG boost also, it had a training time of 1.5 sequential trees and each correct residues, and R is 0.1 and depth 6 KO pose weight and 1.29 for balancing. So support vector machine, which is a linear kernel, it also had training a lot of seconds. That is 742.0 and F1 score, the highest computing cost by the one all our models. And the key nearest neighbors, I had Elsdian and weights distance, where a noise distance, no explicit class weight, minority addressed by distance voting, with a screen score of 3.23 seconds and F1 score of 0.3308. And naive bias, it was not suitable at all, with 0.2 seconds of training and F1 score. ML of neural network, it was not selected with the train, and though it was balanced and it had 13 inputs, dense 64 real LU and dense 32 real U, which means output of one signal. So we went ahead and compressed our base model, that is logistic regression, through the quantization. So through the various techniques: quantization, weight pruning, knowledge distillation, and above all, quantization was the technique we chose. It was the best technique, and we deployed our quantized model because it had the plot of 32 range map of QW and round mean range times the 2556 minus 128 to store as int, and the quantize at inference, which resulted into 0.11 kb to 0.02, 5.3 times smaller. So the F1 score was reduced by 0.0001. So the compression model result summary, as shown in the table, baseline technique, it had a size of 0.11 kb reduced for the model by 1.0. And also the F1 score was 0.42. So quantization, which is the one we selected, it reduced the model by 5.3 times, which is why it qualified. Yeah, so basically this is how the model compression the results were from the metric, and how it reduced or it made the model smaller and the changes it included. So the quantization, it introduced changes like the model size, it made it smaller 5.3 times, and the accuracy introduced 0.0015 and precision 0.001. minus 0.003, recalls minus 0.007, and F1 score minus 0.001. So it over reduced our key metric. And basically, this is it. And thank you for listening. And we really acknowledge our supervisors, Dr. Galiwango and Dr. Yunus. And with that, and the Makerere University College of Computing and the Pago data set. Thank you. Hi there. Yeah, welcome to yet another session. One of my sessions where I take you through my software project